stratigraphy is a technical subject. So I understand that it might seem a lot to take in an hour and a half. And because it's like a house, you build on top of one another. So if it's okay, I'm more than happy to take questions as I go along, because it's very important to understand some building blocks before you go on to the next. Does that make sense? So if anyone's really keen to ask a question and they just can't wait, I might be okay with that. Okay, lovely. All right. So once again, the title is Sequence Stratigraphy. We will look into the subject itself, but the aim of sequence stratigraphy as it was developed wasn't really academic. Sequence stratigraphy was developed by the industry. So the focus or the concept of sequence stratigraphy is really to help resolve oil and gas exploration and production challenges. So that will come across in a lot of the conversations we'll be having. But before we proceed, please allow me to introduce myself so that you kind of get to know me a little bit and my background. So yeah, I interned, my first introduction to sequence stratigraphy started during my exploration geology internship with, yes, Mohammed, please go ahead. Someone raised their hand, Mohammed. My first introduction to sequence stratigraphy was during my internship with Chevron in 1997 at the Lagos office. I worked in the new business exploration and opportunity team. I was introduced to sequence stratigraphy. I finished my geology degree in 1998 at the University of Ilorin in Nigeria. I proceeded to a postgraduate with Robert Gordon University, Aberdeen, which was sponsored by Shell. And then I joined Shell in 2001. And my main task for 10 years was interpreting sequence stratigraphy from wells, core, seismic, and applying the results to supporting exploration, development, and production. And then I moved into the head office in The Hague, where I worked in the new ventures exploration team, applying similar techniques to finding oil and gas in different parts of the world. And then I resigned my appointment with Shell in 2015 to form Rocksolve, which is a geological solutions company, and we still do sequence stratigraphic analysis for our clients to date. In the meantime, I also lecture at the first technical university in Nigeria remotely. I teach drilling and petroleum engineering. I'm a member of a couple of international associations, including American Association of Petroleum Geologists, Nigerian Association, EAG, XP, and a couple of them as well. So that's my background. So let's get into the sequence strats topic itself. Now, the course of this seminar will follow three main subdivisions. The first discussion will be around accommodation space equation. It's very important to understand this concept of accommodation space and the four key elements that play a role in accommodation space equation. It's very fundamental to sequence strat, so that's where we start. I'll try and make it easy to understand because once you get that, that will form the basis for point 2, which is sequence stratigraphy itself. And then we get into it. We first look at parasequences, what are they, and then parasequence sets, stacking patterns, and then we look into system tracks with the T, not the K. Apologies for that. And then lastly, we'll look at how we can then interpret sequence stratigraphy using exploration data sets of well, logs, and seismic. So that's what we hope to cover today. Should be an hour thereabout, and then we have some time for a lot of time for questions as well. As was announced earlier, please note your questions down, write them down, and take note as I go along as well. So let's start with accommodation space. Now, it's very important to understand this concept because, as I said, this is the bedrock of interpreting sequence stratigraphy. So if you don't get these four concepts of that constitutes the elements of accommodation space, what do we mean by that? Well, we do acknowledge that primarily we deposit our sediments in the sea. Of course, we have sediment deposition onshore, on land, but for the purpose of sequence stratigraphy, it's very important to bear in mind that the team at Exxon who came up with this approach were focusing on offshore deposits. So they were looking at deltaic and shallow offshore slope and basin floor deposits. So sequence stratigraphy tend to lend itself as an application to more deltaic, shallow offshore deposits, and not so much application to traditionally land-based or onshore-based depositional environments, such as, for example, our Aeolian deposits or fluvial deposits. You don't really see the application of sequence stratigraphy to that, because that was not the basis for the subject being developed. It was really applied primarily to offshore deposits. So bear that in mind. And that's why sometimes extrapolating, although the principles can be kind of extrapolated back onshore, you can apply some of the principles to deposits that are river systems or Aeolian systems. But just bear in mind that the guys that started it, the Vail et al., Galloway, they were all focused more on offshore. And so that's why this accommodation space equation is always the bedrock. So on the screen, you can see in blue, imagine like the sea, any of the ocean, Atlantic, Indian Ocean, any of them. But notice that in blue is the water depth, as you can see there. Just to check, can you see my screen? My cursor on the screen moving, just to check that. Nick, can you see that? Can you see my cursor moving about? Can anyone hear me? Someone just talk back? Someone just unmute yourself and say something. Oh, can you all hear me? Hello, anyone there? Yeah, just checking. Can you all hear me? Hello? Is that okay? Everyone can hear me? Yeah?
Yeah, we can hear you.
Oh, okay, all right. Sorry, I wasn't hearing, so I thought I've lost the connection. Okay, that's good then. All right, I'll continue. I wasn't sure if you can hear me, so to bear with me a bit there. All right. Okay. So we have the water depth, which is the ocean itself. Then you have the sediment, which is in brown. So you have water depth, you have sediment thickness, which is the thickness of the sediment, which is deposited offshore, as I mentioned earlier. And then the combined water depth and sediment thickness is called relative sea level. This is a very important concept in sequence stratigraphy. So let me repeat it. When you hear the word or see the phrase relative sea level in sequence stratigraphy, you're referring to the combination of the water depth and the sediment thickness up onto the basin floor. Now, the basin floor, from the basin floor to the center of the earth, it's referred to as tectonic. Now, it's called tectonic subsidence, but you could also have uplift. So that, but just for signposting, just take that as understanding that concept that tectonic subsidence is from where the sediment thickness ends, which is the floor of the basin, to the center of the earth. And then the combination of everything is referred to as eustatic sea level. Now, this is where it gets very interesting. So please bear with me as we go along. The first point to note is that the distance between the reference horizon, which is the base of the sediment thickness, which is the reference horizon, and the sea level or the sea surface is called relative sea level. This relative sea level is the accommodation space that is available for sediment to be deposited. So it's very important to bear that in mind. So this concept of accommodation space is base of the sediment thickness and the top of the sea level is called accommodation space or relative sea level. It's the same term. We'll come to that because when we say relative sea level fall or rise, we are using that to describe accommodation space, okay? If you have any comments or question or we just note it down as has been mentioned by our moderator. So this accommodation space is what changes that gives rise to either sediment being deposited or being washed off. So just bear that in mind a little bit, the concept of accommodation space being relative sea level. Next, you have the concept of the distance between the sediment water interface and the sea surface. So the sediment water interface is here and the sea surface, that's the water depth. And then you have the changes in the distance from some choosing reference horizon and the center of the Earth. So the reference horizon in this point is here, and the changes in the distance from that to the center of the Earth. So this could either be called tectonic subsidence or uplift. So you have a choosing reference horizon, and the changes in that relative to the center of the Earth, if the change is negative, it will be subsidence. If it's positive, it will be uplift. And we'll come to that in a minute because these terms are very important for us to understand sequence chart. And so there's kind of like an equation that says the changes here, so the changes between eustatic sea level and tectonic subsidence will be equal to the changes in the accommodation space. So the accommodation space or the relative sea level is the same as S plus W, which is sediment thickness and water. So the thickness of the water body and, the thickness of the water body and the thickness of the sediment, as you can see on the screen, constitute relative sea level or accommodation space, which is a reflection of the eustatic sea level minus the tectonic subsidence, okay? As I said, I understand that there might be some questions and I'm taking my time to lay the foundation. So if you're still not unsure, just note it down and I'll probably come back to that in the Q&A. But this concept of accommodation space is the foundation for understanding sequence stratigraphy. That your sediment thickness and your water depth, that space is accommodation space and is a result of subtracting your eustatic sea level from your tectonic subsidence. So typically, eustatic sea level is relatively stable, but your tectonic subsidence or uplift changes. Other elements move, but typically eustatic sea level doesn't a lot, but we'll come to that in more details. So in summary of accommodation space, sediment accumulation, which is sediment thickness will increase, or you could erode it, which is then a negative, and the water depth, which could increase or fall, could lead to either creating accommodation space or filling it or reducing accommodation space. So does that make sense? So this sediment thickness could move either way. You could increase the sediment thickness, you could reduce it by eroding the sediment, the sea level could fall or rise, and either or could lead to creating accommodation space that you fill or reducing accommodation space. Similarly, when it comes to tectonic subsidence as well. So if you have tectonic subsidence and eustatic sea level, that will be positive, which means you've created more accommodation space. So just imagine if this line, this horizon were to drop here, and that is the new horizon, and that's the eustatic sea level, then you would have created more accommodation space. But if you see, if you have uplifts, and instead of this line here, the line is then here, you reduce the accommodation space that is available for sediments to be deposited into. So accommodation space is not static. It can increase or reduce based on what is happening to the water depth, the sediment thickness, the relative sea level, or the eustatic sea level. Lovely. So in summary, for all this accommodation space discussion we've had, please bear in mind that these are the main drivers for making those changes or resulting in those changes that we looked at. So let's take eustatic changes, for example, which is eustatic sea level from the center of the Earth to the water surface. What can change that? Well, that's a global reference point. So it's not local to your basin, it's global. The eustatic sea level or global sea level, as some authors might refer to it, it's global, but that can change either through one, the volume of the basins, which could be as a result of sea floor spreading, creating more accommodation space for ocean basins, which would then affect eustacy or the global sea level. You could have sedimentation across millions of years. You could have hot, young lithosphere displacing water onto continents, which then increases the eustatic sea level. You could have older or cooler lithosphere, which is denser and retain more water. So a lot of these play a role in affecting the volume of ocean basin. Also, glaciation, both continental and other mountainous glaciation, could affect the volume of seawater. The temperature of the ocean as well could cause the volume to expand. The volume of groundwater being delivered into the ocean as well could affect the volume of seawater. So both the volume of seawater and the volume of available ocean basin has an effect on eustacy, which is the global sea level or eustatic sea level. You also have tectonic subsidence. So a couple of things could affect that. You could have stretching, which you replace light lithosphere with denser asthenosphere, which then stretches and leads to subsidence, because then the lighter lithosphere kind of sinks a bit into the denser asthenosphere, and then you have subsidence, tectonic subsidence. You could create some rift, backhand basin, cratonic basins as well. That is a result in subsidence, and you have more accommodation space created if eustatic changes either stay the same or increases, or decreases, but not at the same rate as you are subsiding the tectonics. You could also have cooling, where the crust becomes denser. You have passive margins and cratonic basins that are cooler, and therefore you have the tectonic subsidence taking place. Also, you could load in an accretional wedge or fold and truss bed, where you load, you increase the load, and therefore also resulting in subsidence or creating foreland basins as well. So a bit of all this technical, I won't call it technical jargon, is just to introduce you the terms that affects eustacy and tectonic changes. I remember here in this slide that eustacy or eustatic sea level changes and tectonic subsidence, those are the main drivers for creating or reducing accommodation space. And when you reduce accommodation space and the rate of sedimentation is consistent with the space you are creating, then you build up sediment pile. Conversely, if you are reducing accommodation space, then that also has an impact on how the sediment fill is. So I hope that it's a bit clear. If not, write down your questions and I'll come back to that later. So now that we've set the tone with the accommodation space equation, we'll now apply this concept to stratigraphic principles. We'll now start introducing terms that then, once you understand the drivers, the global and local drivers for creating accommodation space, we then bring the local driver of the sediment load delivery system. So the rivers or the channels that are bringing in the sediments will then interact with our eustatic sea level, tectonic subsidence or uplift to either reduce or increase accommodation space. We then get filled, and the imprint of all of that is then reflected in the sedimentary fill of the basin. And this is why it interests us in A&P business, okay? So let's go into that. Here are a few basic stratigraphic principles that we need to be familiar with in order to understand sequence stratigraphy. The first one is the principle of original horizontality, which means that initially, where it is tectonically flat, or even if there are barriers, sediments are usually deposited horizontally. These principles are important in order to understand and interpret sequence stratigraphy. The second one is the principle of stratigraphic superposition, which states that the older rocks are at the bottom, the younger rocks are at the top. Of course, we know that when tectonically, this could be inverted and changed, but for the sake of at the time of deposition, this is the rule. The oldest will be at the bottom, the youngest will be at the top. These are the principles. Then the principle of original lateral continuity. Now, this is very important. Sedimentary layers don't just stop suddenly. They pinch out, they taper out. So you are depositing sediments, even if this is the center of deposition, to the side, the axis as well, you are depositing, and the whole thing tapers out. It doesn't just stop like a wall, essentially. It tapers out, okay? That's another principle to bear in mind. So stratigraphy as a subject in of itself refers to the study of layers of rock in order to interpret the geologic history. So you're seeing pictures from the Grand Canyon on the right, and these are hundreds of millions of years of sedimentary basin fill. So we needed to be able to date them, to be able to interpret the history. You know, think of geologists as crime fighters. You know, when a crime occurs, the police come with detectives and they try to peel back history. What happened before? Who was here? Who wasn't there? Now, for example, in the UK, there are a lot of CCTV cameras. So when a crime happens, the police go back and look at CCTV cameras and try and reconstruct who was here before, when. And in some cases, this has really helped in the UK to resolve crime. So that's essentially what we're trying to do with sequence stratigraphy as well. We're trying to almost peel back the layers and go back and go, okay, what was here before, what was there before, what was there before, and we peel it back. Now, there are many methods that we use. We have biostratigraphy, which is the dating of the organisms that were there. So just as policemen will look at CCTV and decide that, oh, Gideon was in that area at the time, and then they'll come to me and say, Gideon, well, we have CCTV camera of you being there at the crime scene by 6 o'clock. What did you observe? We do the same with fossils as well. We look at the fossils and go, okay, this fossil was present at this time. What does that tell us? How was the fossil living? What kind of organism was this fossil? So that helps. But we also have other non-biostratigraphic techniques. Sorry, that N is supposed to be B. That's a typo. Actually, let me just change it now. So that, okay. So we have non-biostratigraphic techniques like lithostratigraphy, magnetostratigraphy, cyclostratigraphy. Time will not permit us to go into all these, but these are other type of stratigraphic dating techniques. It's all the same objective. We use them to achieve the same objective of correlating and distinguishing different layers. And this is very important for oil and gas exploration and mining, because we're interested in the layer that contains our objective, if it is petroleum or coal or whatever it is we are interested in. So stratigraphy is a very important element of exploration and production of minerals on oil and gas. The concept, though, where sequence chart plays a major role is that it then starts incorporating a couple of other stratigraphic principles. For example, the principle of unconformity. What do we mean by that? Well, as shown here, you could have complete stratigraphic successions. So you have today, 10 years ago, 100 years ago. Let's go back to our illustration of CCTV. So let's assume that everything is complete, right? We have all the videos throughout the time up until now to go back. But what if some of these CCTV images have been destroyed? They are not there for some reason. Then we have an incomplete data set to try and resolve our crime. So we do get the same as well. So the principle of unconformity is that, yes, typically the stratigraphic succession follows each other. But for some reason, we have some missing time interval where nothing was deposited. We have no stratigraphic record. Something could have been deposited. The only problem is we have no record of that deposition. Because, for example, as you can see in the picture there is a yellow line which represents a period that is not consistent. So across this yellow line, we have gone from maybe 10 million years to, I don't know, maybe 100 million years to 10 million years. So that yellow line represents either a period of erosion, where all the rocks that have been deposited have been washed away, or non-deposition, where nothing was deposited. That's the principle of unconformity. Any place where there's a missing time is referred to as an unconformity. It's not conformable with the strata that is below and the strata above. They are not conformable. It's not the same time. We can't piece it together. It's not one continuous movie. Something is missing. There's a gap. We also have the law of final succession, which is the principle that fossil groups are succeeded by other fossil groups through time. So if you look at us today, we have Zoom, we have all this technology. This is one time. But if you go back in time, maybe, I don't know, in the past 40 years, there was no technology, no internet. That's another time. And people that were living there are different. And then you could go back another 20 years, you could almost recreate humans or history by looking at pictures of how people dressed. So the same thing with fossils as well, or fossil groups. Through time, they succeed one another. We could look at the picture and go, okay, based on the fossil in this rock is younger or older, this was before or this was after. So this allows us to create zonal subdivision of the stratigraphy and allows us to correlate the rocks throughout the world, which is an amazing, powerful tool. So when you put all of this together, the simple definition of sequence stratigraphy, therefore, is a framework of genetically related stratigraphic fascies and their bounding surfaces used to determine the depositional setting. So let's look at this picture here. This is a stratigraphic picture of, and we'll come into more details of what each of these represents. But notice the original trick track model after Vail, Ito, and Postamentia. These are the guys that were the forefathers, or the guys that started sequence stratigraphy, essentially for all of us. And what the guys are saying is, you have one sequence, okay? And you look at the sequence, and there is a bounding surface at the top of this sequence. There is a bounding surface at the base of this sequence, and then you have the package in between. But even within the sequence, there are other surfaces which are required to interpret the depositional setting. So for example, this is sand, the gray shale. So these bounding surfaces help us to associate the depositional setting with different time. Genetic is time. So a framework of genetically related stratigraphy, genetic stratigraphy, where in the past, for example, in a purely lithostratigraphic sense, someone in the past could have interpreted this sand package to say, you know, that sand, that's different from this shale. Well, yes, purely looking at the lithology. But what sequence strat allows us to do is not focus on the lithology. It's focused on time. So it changes the focus from just purely looking at lithology, but time. It's saying which packages are genetically related. For example, now I live in England. Some of you have joined us from America, from Asia, from India. And although we're living in different parts of the planet, we are genetically related in terms of time. We're both living in 2022. And that's what sequence stratigraphy is about. It's looking at understanding relationship between stratigraphic fascies based on surfaces that are time-bound, that we can point at this time and say, 2022 on LinkedIn or Zoom, a sequence strat workshop was attended by people across the world. That's what counts, is the time that bounds packages, not lithology or other things. And this is a very important concept to grasp for sequence stratigraphy. So you could then see that with that in mind, because we are concerned not just with lithology, we are concerned not just with exact time, but a package. We could then relate and go, oh, okay, you know what? At the time of depositing this sand, you're also depositing this shale. At the time of depositing this sand, You're also depositing this shell. And then you have these surfaces that distinguish different packages that you have deposited, and saying that those packages are related by time. And so we are in sequence stratigraphy interested in, one, the surfaces, but also the geometry, the facies that you've deposited within each time surface. That's what we're looking at. And then you have traditional lithology type, or sorry, a depositional setting like slope fans, low stand wedges, and all of this definition or settings start coming into play based on your understanding of the surfaces and the facie geometries that are associated with them. Okay. So in summary, sequence stratigraphy is the study of rock relationship within a chronostrat framework. Genetically related, just to repeat, and are bounded by surfaces of two things, and this is very important. The surfaces that bound our packages or our sequences are either one of two. They are either erosive or non-deposition. I remember what we called that earlier, surfaces of unconformity. Or the same surface that was an erosion could at the same time be conformable. So what do I mean by that? So at the same time right now, the river Ganges is eroding sediments. But as it is eroding sediments, it is depositing them further offshore. So in our crime scene illustration, while at one time in one part of the planet, erosion is taking place, at the other side of the planet, deposition is taking place. But you can correlate them. They are genetically related. So the sequence boundary, the boundary of our sequences, is either made up of erosion or non-deposition because it was exposed to the surface. The boundary at that time was exposed to the surface, or it's been eroded. But it could also be conformable somewhere else. So to illustrate, here is an example of a sequence boundary. In black here is the sequence boundary. Now notice that this sequence boundary near the surface will be non-erosive. There is no erosion. There could also be no deposition. But further down in red here, you could have erosion. You could have incised valleys being eroded, still the same surface. This black boundary is the same time. And then when you come here into the deeper, you are going basinward, right? Into the deeper ocean, deeper sea, into the deep offshore, the package that has been eroded here by that River Niger or the Niger system is being deposited as the low stand. You are depositing the sand, but this boundary, the sequence boundary, is the same time. And we know that this package is also now covered by another sequence boundary, where on this boundary, sequence boundary, there's even no erosion at all. What you have here are coastal plain sandstones deposited, followed on by shallow marine sandstone, shale, and this boundary there's no erosion. So sequence boundaries are not just erosive surfaces. Don't look for channel calls. Some typically go, oh, sequence boundary needs to have erosion. No, it doesn't have to have erosion. It doesn't have to have erosion. It could be non-deposition, or even their correlative conformities, which is continuous sedimentation in other parts of the basin, typically deeper water offshore. Once again, write down your questions and then we'll come back to them. In order to understand our packages, therefore, we need to have a system of, remember our focus in sequence is sequence, it's about time. So we need to have a method of classifying time. So like today, we use a set of units. So we have seconds, and then 60 seconds make 1 minute, 60 minutes make 1 hour, 24 hours make 1 day, 7 days make 1 week, 52 weeks make 1 year. So we have an hierarchy that builds up into 1 year of different time divisions. Well, we do the same with sequence stratigraphy. We have an hierarchy of different packages that builds up to our sequence or mega sequences. And they are the smallest unit in sequence stratigraphy is the parasequence. So think of that like seconds. Then 60 seconds make 1 minute. So in sequence strat, we refer to a set of parasequences as parasequence sets. These parasequence sets then build up into stacking patterns. A group of stacking patterns build up into system tracts, and a group of system tracts build up into sequences. And a group of sequences builds up into mega sequences. If I just slowly bring you back here, so this package is a mega sequence of 2 sequences, right? And you can see, so that's the first sequence boundary, that's the second sequence boundary, that's the third sequence boundary. So we have 2 sequences, that's a mega sequence. Each of these sequences consists of system tracts. So that's the HST, the TST, and the LST that you can see on here. And we'll talk about that in a bit more detail, but these are system tracts, LST, HST, TST. Now, each of these LST, HST, TST is made up of stacking patterns. And each of those stacking patterns are made up of parasequence sets or parasequences. So parasequences are the foundational understanding of our sequence chart. So you cannot interpret sequence charts in the petroleum industry without starting out with parasequences. That's how you start, whether in outcrop or in the oil and gas industry. Okay, so we start with parasequences, which, as I've just explained now, a sequence or mega sequence can be subdivided into system tracts, which are defined by their position within the sequence and by the stacking patterns of parasequence sets and parasequences. Now, listen carefully because this one is important. Each parasequence set is bounded by marine flooding surface. In my experience of teaching sequence stratigraphy, there are some things that is very important for students to understand, and that's why I stress them a little bit. One of them is the principle that parasequence sets, all parasequences are bounded by marine flooding surfaces or unconformities. So you either have a marine flooding surface or an unconformity. So each parasequence has to have that at the top of their boundary. So you cannot go from one package to another without either a marine flooding surface or an unconformity bounding the parasequences. Okay. Oh, and by the way, just to highlight as well, and there are different schools now. I know there are, since it's an hot topic, there are all sorts of schools of thought, but the 2 main classes or the 2 main divisions are those from the Vail group, the Postamental group, that states that sequence boundaries are unconformities or marine unlap, as the Exxon model, the guys that started it. Galloway says no, sequence boundary should be a maximum flooding surface or condensed interval marine downlap. Now, this is not the class to have the arguments. I just wanted to know that there are 2 schools of thought around that, and some are very vocal around which one they agree with. So bear that in mind. I personally I'm not hung up on any of them. I always look at sequence chart as a means to an end. We are not, as I said, I've been working in industry myself. We're not in the industry we're not academics in the industry. We're not trying to resolve some academic problem. Our job is to find oil and gas. And whichever one helps us is what we focus on. I found that Galloway model of using maximum flooding surfaces as sequence boundary is sometimes easier to interpret. So you could go with that, but I'm also happy to interpret sequence boundaries on conformities and erosive surfaces or their correlative conformities, depending on the system I'm dealing with. I'm not really hung up on the definition. I just need you to be aware of what you are trying to do. which is you are trying to recreate the history and use that to look for where the sand deposits are likely to be. That's what we are in the business for. Whether we call it maximum flooding surface or unconformity, as long as you can understand what you're doing and you can explain that to your colleagues who do not understand sequence stratigraphy, you can help them to understand why you said this is where the sand bodies are likely to be. This is where we should focus for exploration and all that. That's what's important, okay? Brilliant, all right. So I haven't defined parasequences as our building blocks for sequence chart. Let's take a look at a couple of examples, all right? Remember what I said earlier that the flooding surface, something called a flooding surface, which is the marine surface that defines the top of a parasequence. It's important that you isolate that in your interpretation. As I mentioned earlier, parasequences are the building blocks of sequence stratigraphy. So you can't not carry out sequence stratigraphic interpretation without starting out with interpreting your parasequences. So parasequences by definition are relatively conformable succession of genetically related beds or bed sets bounded by marine flooding surfaces and their correlative surfaces. And this concept of correlative surfaces always comes up in sequence chart because when I've had to work with less experienced geologists, some of them are a bit hung up on the definitions and they get themselves tied up in a knot and going, oh, well, there's no flooding surface. I can't see the flooding surface on seismic. I can't see this flooding surface on my well. But you can then look for your correlative surface. So is there any other indication that even though it's not showing itself up as a flooding surface based on one set of data, could you correlate that surface to a flooding surface somewhere? It's very important to get at the back of our mind that it's bounded by marine flooding surface and their correlative surfaces. Because what is marine in some parts of the planet at the same time could be onshore. So for example, today I'm on land somewhere in England, but the flooding surface that correlates with this parasequence is offshore, is off, I don't know, Southampton or Portsmouth. But in the next 100 million years, this surface is a parasequence top because it correlates genetically with another parasequence set that is formed in the marine setting. Does that make sense? So what it means genetically, therefore, what I'm trying to explain is that all the fasces within a parasequence were deposited in lateral continuity to one another. So that means the sands that are being deposited now in this parasequence set is the same as the shale that was being deposited offshore, but they are genetically related until something else tops all of them. So if you look at this parasequence sets here, oh, let's go back. If we look at this parasequence sets that I've got here, so you have one flooding surface and another flooding surface. Now, this is very important, the concept of shallowing upward. So please bear with me as I try to explain that. Remember I said earlier on that each parasequence set is bounded by a flooding surface and their correlative surfaces. So we have a flooding surface here at the base. So you have this coal, this coal, which is, this whole package is fining upward. Now, and this is another important point to bear in mind. When people interpret sequence chart, for those who are working in this space, they look for fining upward and coalescing upward. Now, in sequence stratigraphy, we're not interested in finding upward or coalescing upward. Finding upward or coalescing upward doesn't tell us the total story. What do I mean by that? We are interested in depositional setting. Finding upward or coalescing upward is a log interpretation, a log motif. You could have a finding upward sequence or a coalescing upward sequence that has happened in the same depositional setting. So the fact that your log is finding upward or coalescing upward in of itself hasn't answered your question around sequence stratigraphy. So I get people hung up and they, oh, Gideon, I've interpreted these, is all finding upward or is all coalescing. I said, you guys are mixing things up, okay? Whether it is finding upward or not is not what defines a parasequence set. Once again, what defines a parasequence set is a flooding surface. So what you need to look for is one flooding surface and another flooding surface. Now listen and listen carefully. It is very important that within each parasequence set, the whole circle is shallowing upward. Now, what do we mean by that? That is not the same as fining upward. Shallowing upward means that from one flooding surface to another, you progressively would have shallowed from a depositional setting point of view. You always go shallowing upward. So the depositional setting will always be shallowing upward to the next flooding surface. So for those, please bear with me because, as I said, sequence strat is a bit specialist. It assumes that you are comfortable with a lot of other parts of geology like sedimentology. But if you are not, don't worry, we'll still try and carry you along a bit today. So what do I mean by that? So you look at this parasequence set, all right? You are going from subtidal to swamp. So essentially, you are going from deeper depositional setting to a shallower depositional setting to a shallower depositional setting and to really shallow. So because of that, this whole parasequence set is shallowing upward, although it is fining upward. Now, this distinction I'll spend some time in explaining, because something, because it's fining upward means we are going from shallow to deep. No, you can go fining upward, but you are shallowing upward. So each parasequence thread must shallow upward. That's the definition of parasequences. That's how it works. Now you come to this other parasequence set, which is coarsening upward. Now, some equate coarsening upward to shallowing upward. No, it doesn't. In this case, it is shallowing upward because you move from offshore to transition zone to shore face to foreshore. So what is important for us in sequence stratigraphy is not the log motif itself, but this interpretation of the depositional environment. So whether it is fining upward or coarsening upward, you want to interpret the depositional environment of the packages and ensure that for each parasequence set, you're going from one flooding surface to another, but the whole set is shallowing upward. Okay? So once you do that, and this is a very good example, once you've done those parasequence sets, you now start stacking them together. So you stack parasequences on top of one another and laterally, and then you start interpreting the lateral expressions of those parasequence sets, and that takes us to the next building block, which is stacking patterns or parasequence sets. Now, for stacking patterns, there are a couple of words as well that we'll now start talking about. Now, bearing in mind these points as well, which is a similar point I was making, there are three main stacking patterns: progradational, retrogradational, and aggradational. Once again, people mix up these terms, so please bear with me. Progradational refers to the movement of the shoreline. So you have a depositional setting, and over time, remember that accommodation equation thing we started with, the water level, the shoreline where the system, the deltaic system bringing in your sediment. By the way, remember, bear in mind that sequence strat was based on the book leaf succession in Utah, in America, and I've been there a couple of times. So that deltaic system is what guides some of the terminologies. So we have to understand it from first principle before we start playing around with it. So progradation is you bring for a variety of reasons, you bring the depositional setting, deltaic, in contact with the sea level, and if that shoreline is moving basinward, is prograding basinward. And the best way to look at it is look at this example here that I have. So from here, you have this outcrop. Let me do this. Okay. So you have this outcrop, right? So you take a log there, that's outcrop A, you go there, outcrop B, and outcrop C. If you look at this outcropping system, you will notice that the shallower the positional environment, shallower fasces are progressively deposited more basinward as the succession. So which means that your parasequence sets are shallowing. So you have one parasequence. So each parasequence set shallows, each parasequence shallows. But when you take that parasequence and place another parasequence on top of it, the parasequence set above your parasequence 1 is shallower, depositional wise, than the one below it. And the only reason why you could place a shallower parasequence on top of another one is because the sea level has receded. So imagine if today, this is where the deltaic system is and the marine shale are over there, where the only way you put another deltaic system on top of this is if the shoreline has moved for the next section. So progressively, the shoreline is moving as you build up, and each parasequence set taken at one point is shallowing. I hope that makes sense. If not, note down your questions. And then when you look at this package, you can see that each progressively, although it's going offshore, each package, parasequence, this is how you interpret it, is each package is shallowing. And why would that be? Well, the reason is accommodation space is being filled faster than its creation. Remember that water depth thing? So you're chewing up all the space that is being created faster than it's being created. There could be many reasons for that, but what we're interested in interpreting is that the accommodation space is being filled faster, so the whole package, the parasequences are prograding. That's one. So the other option is the reverse of that, where the parasequence sets are retrograding. That is, you have one parasequence set that is shallowing upward, remember, bounded by our flooding surface. The next one on top is also shallowing upward, but is made up of deeper marine or deep marine fasces. So here's an example. You have shore face sandstones at point 2, 3, and 4. You can see the shore faces in prograding out, and these are the transition zone and the offshore. But you come here and you have the shore face sandstones being overlain by transition zone, which shows that the sea level is retrograding, is coming back more inland, and you are therefore depositing deeper fasces over shallower fasces. And then you have a gradational parasequence sets, which is a stacking pattern where there is not a lot of change between the fasces below and the fasces above. It seems to stay the same, which means that the sea level has not been changing. What does all of this tell us? Well, all of this tells us that this interplay of sea level movement is linked to accommodation space. If there's not been a lot of change in accommodation space creation, that means you are creating enough accommodation space as you are using it up, then you have an aggradational parasequence set. If you are creating more accommodation space than you can fill, you have retrogradational. If you are creating or you are using up more accommodation space than you've created, you have retrogradational parasequence sets. So those are the parasequence sets. How does this then feed into our system tracts? Each of what I've described, the stacking patterns, adds up to our system tracts, okay? The first system tract we look at is the high stand system tract. The high stand system tract is similar to our aggradational parasequence sets in the sense that there's not a lot, there are, but not a lot of changes in the accommodation space being used up. So the accommodation space creation stays relatively the same. And so fasces or parasequences just stack up on top of one another without no relative change in whether it's shallowing upward, it's shallowing on top of one another or deepening. And that parasequence set is then usually, oh, by the way, there are also different schools of thought around the number of system tracks. There are these 4 system track model. There are the 3 system tracks model. I'm more a 3 system tracks model guy. This whole falling stage system track thing, I know some authors refer to it a lot, but I'm more than happy to just go with low stand, transgressive, and high stand. Okay, I think that makes life easier for all of us in this space. Okay, so when you look in here, you have the high stand system tracks, and then you have a situation where the sea level begins to drop, and you start prograding out, and you start depositing. The yellows are the shallow marine sandstone, which are reservoirs. You start, because you don't, in my experience, we don't really see a lot of falling stage system tracks represented in the rock record. That's why I'm more one of those school of thought that goes for this one, for the sake of making our life easier. Honestly, I will tell you not to worry about it. Academics might do, but in the industry, really, we don't really see them in the rock record. They may be, but not so much. So you have this surface of forced regression. What do we mean by that? Well, what we mean is a bit like progradation. So you can see the fasces building out into the sea. So you have like a forced sea level drop. So you see that drop. So things are prograding more into the sea and the sea level is dropping. It says in here that it's important to bear in mind that in this stage, the parasequences may miss the flooding surface. Anyone has an idea why? Any idea? Because of erosion. So you have, imagine this parasequence set with this forced parasequence set. Because of the forced regression, the system builds out, erodes the flooding surface out, deposits the next parasequence, the next one comes in. Because of that regression, you are cutting up and eroding the flooding surface. So this is where experience comes in, because I've had people go, oh, but I can't see a flooding surface. So that can mean that all this package is one flooding parasequence. I said, yes, but remember the definition again, that a parasequence set could also relate to its correlatable conformities. So you then need to use a combination of tools and understanding of the principles to say, yeah, okay, that's missing because a flooding surface is missing on this parasequence because it could have been eroded away because we are in the forced regression falling stage system tracks, okay? And then at the end of that, which is this point, this red, you then now start building out a low stand system tract. The base of that low stand system tract is our sequence boundary. So if you look at the chart on the left of the forced stand track model, the end of the falling stage and the base of the low stand is the sequence boundary. So this is one sequence or part of one sequence, not a complete sequence. And now we are starting a whole new system with these system tracts. Now, so bear this in mind, this red line correlates to sub-area erosion and exposure. So essentially, you've dropped the sea level, you've eroded things away, and now you start depositing them. So the line, this black line, which is the base of our low stand system tract, corresponds to this sub-area erosion and exposure, which is the top of this falling stage, to be the beginning of one sequence. And that's the sequence we are going to build up now, okay? So you then start building up, continuing in a progradational system, not a forced regression, but a progradational system where the coastal plain fasces are progressively building out, and you have this shallow marine sandstone also progressively building out. And this package is called a low stand system tract. Technically, as we explain it in sequence stratigraphy, it could be, as I said, there could be many reasons depending on where you're on the basin. The rate of eustatic fall is so slow that it equals the rate of subsidence, which is then exceeded by the rate of subsidence, leading to a slow relative rise in sea level. I know this might sound a bit law, but just bear in mind that there's this fine interplay of sea levels to create accommodation space. To create accommodation space, sea level always has to rise. The question is, what is the relative rise? It is that relative rise that develops into system tracts. It's not possible not to have a relative rise. You need to have a relative rise in sea level to create accommodation space. It is just relative to other systems that gives back to our conversation. You can note that your question on this as well. So this slow rise, so you have always, bear that in mind, you always have relative rise in sea level, but when that slow rise is outpaced by the sedimentation rates, we then build out our low stand system tracts. So the sea level is rising, always rises, bear that in mind, but the sedimentation rate outpaces that relative rise such that accommodation space is not created enough. It's being created, but not enough to accommodate all the sedimentation that the system is bringing in. And so we build out a low stand system tract. And then once you reverse that, let's say by eustatic sea level rise, it increases. The rate of relative sea level rise also increases such that the rate of sea level rise now outpaces the supply of the sediment. You now start back depositing the fasces, and you build out what we now refer to as a transgressive system tract, which is the sea level is now transgressing onto the land. It's good to bear in mind. And that's how you create a retrogradational parasequence stacking pattern. So remember that our LST that we built up earlier, you now have oops. Oh, what's this? Okay. So you now have the base of the transgressive system tract is called a transgressive surface of erosion, or TSE. What do we mean by that? So remember what we said about you have your LST, okay? And for your LST, the sea level, the relative rise, remember what I said, sea level always rises. The relative rise to sea level is slower than the sedimentation rate. And so the sedimentary system erodes and builds out. When you then reverse that, where the relative sea level rise is faster than the sedimentation rate, you reverse that and you have a surface that we refer to as a base of TST, or transgressive surface of erosion. We then slowly now build out to still deposit coastal plain, but notice that here the coastal plain is much deeper in the system, maybe on the slope, but then further back, because the sea level is now rising, you push all of that deposition back here. It does not necessarily mean that there is erosion, as we call it, like a cut. It just means that it's a term that we use to represent the fact that, and we do see it in seismic or on logs, as a transgressive surface of erosion. When you've built up to the top of that system, the top of that transgressive system tract is called the maximum flooding surface. And then things quiet down after the maximum flooding surface, such that the rate of eustatic rise slows down enough that the rate of sedimentation slightly outpaces it and builds up into a progradational stacking in the ice stand system tract. So the turnaround from retrogradational stacking pattern in the transgressive system tract to progradational with a bit of aggradational as well is what builds up our ice stand system tracts. And then we repeat that and you have a complete sequence. So there you are, one ice stand. If you're Galloway, you go from maximum flooding to a sequence boundary. That's one sequence boundary there, one sequence boundary there, FSST, falling stage, low stand, transgressive high stand, and then another falling stage. Now listen to this. This is very important. Not all system tracts are present at any given location. How about some of the more younger geologists tell me, oh, I can't see the LST in this case, or yes, it's true, it's expected. So don't expect to see all of this complete sequence in everywhere you're working. Sometimes you could go from HST to HST, sometimes you go from HST to QST, no LST, no FFST. Bear that in mind, because that's the reality of the situation. But this is the model, this is the understanding of sequence stratigraphy. So in summary, we have scale in sequence stratigraphy. As I said earlier, it's a lot, so I will just kind of wrap up sequence strat. I won't spend too much time on this, but similar to everything I've explained earlier, this as well. Let's just go into how we apply it to exploration and production, so that I can get this over in another 5 minutes, so that we can take questions now. The oil industry is like real estate, really. You acquire a property, you develop it, you collect rent, to sell the oil, you maintain it. So for geologists in exploration, we're always deciding which country are we going to explore in, which basin are we going to explore in. This is a map of Nigeria, showing the many sedimentary basins. If you want to explore in Niger Delta, which block are you going to explore in, or which marginal field should you buy into, and all of that. You do some studies, you do seismic stratigraphy, you integrate everything we've explained today to kind of look for where the sands are likely to be. You drill a well, you find some oil. You want to go back and look at the reservoir, what depositional setting is it, and then you develop a field. You want to look for which one is source rock, which one is reservoir rock, how are things migrated, which area should you focus on, seismic interpretation, correlation, everything we do, plate definition, regional studies, they're all underpinned by sequence stratigraphy if you know how to do it. Now, everybody does it that way, but if you do, it's a massive, massive advantage. And then you apply that to reservoir modeling and solving production geology problems, as you've seen in this example that I worked on. Okay, so how do we interpret sequence chart in the industry? Well, first, identify the surfaces. The maximum flooding surface, the sequence band, which one can you identify, okay? And then look at the geometries, go from the oldest to the youngest, backstrip it, okay? So this was before, and then reassemble them to interpret the evolving character of the positional setting. That's essentially what we're trying to do. And the way to do that is we use well logs, 2D and 3D seismic if you have it. You look for those surfaces of erosion and non-deposition. You look for flooding, transgressive surfaces, blah, blah, blah. You integrate all of these logs. You look for your maximum flooding surface. In the seminar, these are the kind of things we do practically, okay? The 5D seminar we involved was actually looking at examples, data sets, and really carrying out the interpretation and getting an hands dirty, because that's the best way for you to really understand all of this. Everything I've explained is when you start doing it yourself under the guidance of someone that says, okay, no, that's what we're doing. You start acquiring. I mean, like I said, I've been doing this for, 10, 15, 20 years now. And so all of that comes with time. And that's an example of a log correlation panel. You kind of like, this interpretation typically would have been different, but when you use sequence stratigraphy, you start, this is like an outcrop. This is an outcrop actually in one of the ones that the guys looked at. And that's an example of how to interpret maximum flooding surface. As I said, we can't go into that today, but just to give you an idea of what you look for in logs, how you interpret them, sequence boundary in seismic and logs, what to look for, and and that's what it is. And then these are also examples of how you interpret sequence chart with the logs, grain sizes, the positional settings, and you build it all up into the stacking patterns, low stand classic stacking, transgressive classic stacking, high stand classic stacking as well. And then this is seismic stratigraphy as a whole subject on its own, a whole course on its own, where you look for these features, these geometries, termination geometries that will help you to interpret your sequence stratigraphy from seismic. And those are examples of them. And yeah, and I would like to kind of round up here. As I said, the other bit about interpreting it, that's a whole another 2 or 3 hours of lecture. So I'm short of doing it yourself, unfortunately, I can go on and on and talk about it, but you really need to kind of get your hands dirty and learn from it. But my focus for this seminar is to introduce you to the subject, is to help you understand the building blocks, the key terminologies, what they mean, and what we're trying to do. And the original intent, remember, was to increase the ability to predict hydrocarbon occurrence in the subsurface of frontier areas. This was what the original intent was. And for someone like me that has worked in frontier exploration or exploration, this is what it's about. I help us understand the relationships, create a framework for understanding the relationship based on our observation using set criteria. And I can tell you it works. I've used this for 15 years thereabout in my career, and I can tell you it works, but it calls for a lot of experience. Because as I said, it's not one size fits all. You need to understand the fundamental and then how to apply it. And then it helps you to, what I like about sequence chart is that it helps you to bring everything together, log, seismic, outcrop, core. You bring all the data sets together using one framework, biostratigraphy, all the stratigraphy as well, and you have one explanation that is consistent. And it allows us to have the geology framework to create play maps and understand the spatial and temporal stratigraphic variation in terms of our GDEs or ground situational environments. So thank you, everyone.